Hey there. So let's take a look at where we left off earlier today in class. We're talking about the bomb calorimeter. And we had a question earlier that I mentioned I'd get back to you on, so let's talk about that. And that's the equation for the bomb calorimeter. So going back to this slide, we see an image of the bomb calorimeter and how it's that metallic insulated combustion chamber. And here it says weighted reactants are placed inside the steel container, but we're tracking the temperature change of this surrounding water. So it's, in a sense, an indirect measurement of the heat exchange, the heat that's being produced from the reaction that we're studying there inside the calorimeter is being measured by observing whatever happens to the temperature of the water. So here we see the equation here is Q equals C delta T. The M that we saw in the equation prior is not here. So I made an explanation here on this slide for you all. Where's mass? Okay, so the M mass is not used in calculations with the bomb calorimeter because you're measuring the heat released by a system and you're measuring that via the water inside that calorimeter. So usually with the bomb calorimeter, it's not one substance. We usually have a mixture or a reaction. And so with that, we don't have a way of measuring the mass change as the reaction progresses. So the reaction doesn't just happen in one moment. There's usually steps that we mentioned earlier where we can have a transition from reactants to products. And so with that, we don't have a way of measuring with that reaction the mass change throughout that process. So we're going to leave mass out and just say it's just a constant because we're just tracking the change in temperature of the water. So it's an indirect measurement that way. When we look at a coffee cup calorimeter like we did in the lab today, we do need to include the M there, the MC delta T for a coffee cup calorimeter experiment because we're looking at how much one substance gives off in heat. So it says here a specific substance. So what we were doing there is we were tracking the pure water that we used. And so that's the big difference here in types of calorimeters. And so if you're given a question like the example we saw, where it says you're using a bomb calorimeter, just remember, keep mass out. And so with this equation, we looked at this example, in class earlier today. We were given 2 grams of octane. They gave us extra information. Because it's a bomb calorimeter, we're just going to ignore the mass. And so here is the work that we discussed for this problem. It's just going to be Q equals the specific heat, C, of the calorimeter, not of octane, and then the change in temperature of that surrounding water. Note it says that in the question here. The surrounding water is increasing, not the octane change. Okay? And so because of that, we're leaving mass out. And we calculate by plugging in. Okay? Here we have the similar calculation, the same reaction as previous slide, but we want to figure out the energy of combustion per gram. So now it says per gram. Now we can utilize the grams given here because they're asking us not about the reaction, they're asking us about that substance. And so here, what we're going to see is the value we got as an answer on the previous slide. So we're saying if that's our energy per reaction, and if we're assuming we have 2 grams, here's where we can just use that calculation to figure out the energy of combustion per gram. Okay. Previously, I'll go back again. Okay. This was just a measurement of the change in temperature of the water that's around the container where our octane is. And so we're measuring indirectly, knowing the fact that our surroundings, our water here in this case, is going to be equal in magnitude to what's inside of that container, the octane inside, which would be our system. Right? So then when they ask us per gram, that's when we need to look at the actual substance. So we're saying for the reaction itself, we've calculated it's minus 106 kilojoules. That's for 2 grams, right? That's what we originally had in there. So we're going to divide it by 2 to figure out how much it is per 1 gram. That's what this question's asking, per gram. So just a simple division, we get that answer. What's the energy of combustion per mole? That's also called the molar heat of combustion. So for that, we want to take our amount per 1 gram, and we want to calculate the grams for octane. That would be per 1 mole whenever we add up the values from the periodic table. So 8 carbons plus 18 hydrogens, we add all those values up, we get a total mass of 114.26 grams. Whenever we add up the atomic masses off the periodic table, that's always per 1 mole of that substance. And so what we're doing here is we're canceling grams out. And we're going from kilojoules to gram to kilojoules to mole. The mole will not cancel. It's showing up as our product, our unit for our answer. And that's what we're asked about. So then we just multiply straight across the negative 53 times the 114.26, and we get this value. Again, I mentioned I put it in scientific notation. I'll put together a brief review, if it's been a while for you, on how to go from a large decimal number, whether in this case it's very small, much less than 0, or a number much greater than 0, how we condense that into a scientific notation. It's just a shorthand. Okay, so we'll go over that. All right, so then we ended up with enthalpy. And so just to briefly review that, we were given another equation, but looked very familiar from what we talked about before. Here we're putting in H for our enthalpy value, the sum of internal energy, so we see our E there from very early in this slideshow, and then pressure and volume showing up as well. So let's go ahead. We did this example before. I'm going to just breeze through that one. We talked about endo and exothermic, what each direction means. So I'm going to go past that. We did example 7 together. I'm not going to go and review that again. What we need to do is get to right here. So here's, we did the review on why mass was left out of the equation for a bomb calorimeter, and now here we're arriving at the coffee cup calorimeter, the one that you used in the lab today. So here, let's take a look. Reactions are carried out in aqueous solution, so we know that we're going to have substances that are not pure, and the calorimeter is an insulated container, but it's not purely insulated from the surroundings like the bomb calorimeter was. We do have, an imperfect seal here with those styrofoam cups versus the metallic bomb calorimeter. Okay, we will be using the mass of the solution. Notice the subscript there, and then the heat capacity, the specific heat capacity of the solution. So you really want to follow those subscripts to make sure you're using the data correctly. The data from what part of the experiment. Look at those subscripts to help guide you there. We're going to assume it's constant pressure, and so we have our Q of reaction is going to be equal to our delta H for the reaction. Okay, let's take a look here. We have this example. We have two stepwise, we have a stepwise reaction here, and what we've done is we're trying to match our reaction that we want in the end. And so to do that, for example, here we needed to multiply this second reaction all across by number 2. So just to briefly clarify, we need to multiply the delta H by 2 if we do that, to keep both sides of the reaction even. And if we need to reverse a reaction for any reason, we have to reverse the sign of delta H as well. All right, so let's look at example number 9. Actually, we did this in class, right? We talked about this one also before the lab. And the way we were able to determine which value of Q fit which type of calorimeter was remembering that with the bomb calorimeter, all of the change in internal energy is all heat, whereas the coffee cup calorimeter is not completely sealed up. Some of that change in internal energy is going to be done as work, so we are going to have a lesser value. This question says it's the same reaction, same amount of reactant conducted in each of these types of calorimeters. So all this question is showing as this example is the fact that the coffee cup calorimeter will have some heat loss due to work. So that's all this example was to show. All right, so here's where we get into the example prior. Why would I need to multiply a reaction by a specific coefficient? Why would I need to do that? Well, not all chemical reactions occur in one step. Most reactions occur in a series of steps. We call those intermediates, right? So we have our two reactants we start with, we put them together, the reaction begins. It may have 1, 2, 3, 4, or many more little steps that create little intermediate products that are not the overall product we see in the final reaction, but they form, then they're used up as a reactant in a following step, and so then they're converted into a final product. So we have stuff that appears for a moment and then reacts again that we don't see usually when we talk about a chemical reaction. Here we're going to look at those steps and something we call Hess law. So all Hess law says is add up all the steps, you get the delta H for the entire reaction. Okay? So this is just a slide reviewing again. Can't stress enough that if you need to multiply by a factor for a reaction, it needs to go to that delta H value that's either given or that you find in the appendix. So let's take a look at this example. We have example 10 here. Okay, we were given the following data. We have a reaction here. We've got fraction coefficients. Don't worry, it's okay. Right? I know that might look very weird. You don't usually see that that often, especially in intro chemistry, but it's going to be okay. It's going to work out. All right, so we just have fraction coefficients here. Let's see where it takes us. We have NH3 on the product side. That's ammonia. And it's a decomposition reaction because we only have the one reactant to start with. So it's breaking apart into the components, nitrogen gas and hydrogen gas. And we're also given a delta H for this decomposition reaction at 46 kilojoules. All right. We're also given a second step. We have the formation of water. Okay, so this is a synthesis reaction with hydrogen. We have 2 moles of hydrogen reacting for every 1 mole of oxygen. And as a product, we're getting 2 water molecules as our product. Then we're given the delta H for this synthesis reaction as negative 484 kilojoules. You're going to be given in these types of problems to take that data and manipulate it into what we're going to call a target reaction, so an end final reaction. We want to combine those initial steps we were given up at the top and make this final reaction you now see at the bottom. So we want to keep track of who's a reactant and who's a product for this overall reaction, and we're going to try to manipulate the steps to match. So here we see that N2 gas is on the reactant side. Well, our original step reaction that was given up here, the nitrogen gas was on the product side. So we can already see we're going to have to flip this reaction to get things to line up to the right side of the reaction, right? So that's one thing to pick up on. The other thing to pick up on is when we look at that nitrogen 2, it was given as a 1/2 coefficient. Our target wants the coefficient to be 2. So we have to manipulate that coefficient somehow, and we're going to use that by multiplying. Here's the strategy when doing these problems. You want to go to that required reaction, that target reaction, and just kind of pick it apart like I just demonstrated there. Starting there, what particles are showing up as the reactants, which ones are products, Okay, we're going to reverse reactions that were given as the steps so that we have them line up correctly with this target reaction, and then we're going to do any kinds of multiplying with coefficients that we may need to do to get those to match. So this is what it's going to look like. To match that target reaction that we're given, we need to flip both reactions actually. So now we went from a decomposition reaction of ammonia to a synthesis of ammonia. Ammonia is now a product. I didn't change these values yet. You can go back and see. They're still the same coefficients. We didn't do any multiplying yet. But I did reverse the reaction, so I needed to reverse the sign. You'll recall this was positive initially, so now it's a negative 46 kilojoules. And originally we were given water here as a synthesis reaction, but now we've flipped it to get water on the reactant side, so now we're showing as a decomposition. And so in doing that, we need to flip its delta H sign as well. This was originally negative 484, now it's a positive 484 kilojoules. And so here's our target reaction again. So now compare what we have on the reactant side. We have nitrogen here in our first reaction. Nitrogen is given on the reactant side as our target. So that's lined up. We'll get back to the hydrogens in a second. The second reaction, we have water here as a reactant. We look at our target. Water's on the reactant side. That's matched. That's lined up. Let's go back up here and say, okay, here's my yield arrow for the first equation. So we have the NH3, the ammonia, is on the product side now. We look at our target. Here's my yield arrow. My ammonia is on the product side. That's lined up correctly. And then finally, the oxygen is now showing here on the product side of my step reaction up here from flipping it. And we want it on the product side when we match our target. Okay, so now we just need the numbers to match now. So we have the components lined up correctly, and we have our delta H signs changed appropriately to show that. What we need to do now is manipulate these coefficients so that we have things cancel out that we want, and we have others match that target. So here again is our target. We want 2 as a coefficient for the nitrogen. We start with 1/2. Okay. We have 6 as a coefficient for the water. We're starting with a 2. Okay. So just like balancing equations, we have to think, what do I need to multiply this entire equation by in order to get the coefficients of that target reaction? And this is what we would end up needing to do. We would need to multiply the entire first reaction by 4. So half of 4, or 4 times 1/2, gives me 2. So that's why we're doing that step here. The 4 times with the H, we'll see that in just a moment. I will show you hydrogen at the end. But then that 4 is going to also go to the product side. 4 NH3 will show up here, which matches my product for the target, right? So that is so far the nitrogen and the ammonia. We've matched those coefficients. We need to multiply the delta H as well by 4. I'll show you what we get for that on the next slide. Let's look at the second reaction now, our decomposition of water. We have a coefficient of 2 in front of that water molecule on the reactant side. We compare that to the water of our target. We have a coefficient of 6. So to go from the given 2 to 6, we're going to need to multiply the entire reaction by 3. So we'll carry that across. 3 times 2, we get 6 water. 3 times the 2 hydrogen here, we'll get 6 as well. 3 times the 1 oxygen in our original equation. Check it out down here at the bottom for our target. There's a coefficient of 3 there. So that just carries down. And again, stressing again, the delta H needs to also be multiplied by 3. So you want to think of it as a balance, like when you're balancing equations in chemistry last year, or even looking at it as an algebra way. Whatever you do to one side of the equation, you must do to the other in order to keep that balanced. So all we're doing here, we did not change the reaction at all. We're just changing the amounts, okay? It's consistent from reactant to product side, so we're not altering the reaction at all in doing that. Here's what we get. Our final 2 reactions from multiplying those numbers through And notice I've lined up here the two yield arrows. Because these are kind of offset from each other, lining them up on the yield arrow will just help your eyes when you need to look from top to bottom. We're actually going to like add slash subtract components of these two reactions, see what's going to cancel out and go away and give us that overall reaction, right? So we want to line these up so we can do a simple subtraction. All right. We're going to carry down the delta H's when we do that. Here's our net, our reaction delta H that we get, just adding those two together from those two steps. And then the target reaction there showing up. And so what I had to do that, here we are, those red lines indicate how the hydrogen on each side of the arrow, you'll notice in this reaction, the 6 hydrogen molecules are on the reactant side, but the other reaction, the 6 hydrogen molecules are on the product side. So when they're on opposite sides of the reaction and they're the same number of moles, same chemical, in this case H2, you're going to cancel them out and they're going to disappear from the overall reaction. So take a look down here. Our target reaction did not have hydrogen by itself here, and this is why. It's canceled out being on opposite sides of the two stepwise reactions. Okay, so that's what we get for our response, our answer for example 10. All right, so moving on for the rest of chapter 7, we need to cover some more terminology. So you'll see a lot problems saying that it's under standard conditions, standard properties. So the standard state refers to a series of conditions that are normal, unadjusted atmosphere. So we were in the lab earlier today. That was just done under room temperature, right? We didn't change the temperature of the room. And so that's given as about 25 degrees Celsius. If it was something that really was going to take more of an important role into our reaction today, we would take a specific measurement of the room using a thermometer in the room. We didn't need to for the experiment we did today, but standard conditions are defined as room temperature. In Celsius, that's 25 degrees Celsius. It's roughly 65, 67-ish in Fahrenheit. And we're also going to have the understanding that we're under normal atmospheric pressure. So I mentioned earlier today, the pressure of the atmosphere that we feel normally, that's on us. Normal Earth atmospheric pressure is defined as 1 atmosphere. So that is a standard condition. And lastly, if we're talking about solutions that are in a reaction and it just says standard conditions, then that's understood to be 1 mole. 1 molarity of that solution. Okay, the way that that's going to be signed to you in a problem is you're going to see this little degree sign. That little degree sign tells us it's under standard conditions. Okay, so you may need this extra information of the 1 atmosphere pressure or the temperature being at 25 degrees C. You may need that information because it's not spelled out in the problem for that environment. That little circle there that looks like a degree symbol, it's not. That little circle there in this case means standard for standard conditions. If that's absent and we just have the delta H, then standard conditions are not assumed here. You want to look at what else is given in that problem to get the information you need. Okay, so we have the standard enthalpy change, but now we're going to add a subscript as well, and we'll get standard enthalpy of formation, the formation showing up as that subscript lowercase f. Okay, and so we have a definition here. That's the enthalpy change for a reaction forming 1 mole of a pure compound from its elements. So this will be from just the elements. We have a synthesis reaction, and we're just getting 1 mole of a product. So just very simple, small reaction. The elements have to be in their standard states. And so if you need to look up the delta HF values to use in a problem, you'll need to consult the index, the appendix here of the textbook. Here, I'll show you what it looks like in our class textbook. If you have this, you would go to the very back. Okay. And let's see, it says page A5. That really doesn't help with a textbook over 1,000 pages big, but what we have here, sorry, the page is wanting to close, is on this page you have different data up here with atomic sizes, but then down here at the bottom of the page, sorry, I'm trying to line up with the camera there. It's going to take me a little bit of practice to get that. It says standard thermodynamic quantities, and so we want to look at the delta H column, and for here you'll notice it does have that delta H0, so this is the standard states. And so when you look up different elements, you'll see those atomic symbols for them. You'll have your delta HF there. If you don't have the textbook, I will see if I can find a table that looks very similar so that as I make quizzes and make exams, you'll have like the same columns in the same order and the same format so that it's not tricky to anyone, as you're using them. So I don't want to throw anything in there to make it confusing or a disadvantage to anybody who doesn't have the textbook. Okay. For a pure element in its standard state, we have a definition here. It's going to always equal delta HF 0 kilojoules per mole. And so you'll see that for elements when you look at them in that appendix data table. All right. So in our textbook, it's called Appendix 2B. Because this definition requires 1 mole of the compound to be made, the coefficients are going to be fractions. It's okay. Let's take a look at it. Okay. So then we have calculating the standard enthalpy change for a reaction. Well, this is for formations, okay? So this is when we're using those coefficients. There's fractions there. We're talking about the entire reaction. We have elements that are our reactants. So you're going to recognize just elements being there, forming products, okay? We can use the following equation. We have delta H0 is how that's read, delta H0 or delta H standard for the reaction. This is a Greek sigma symbol, and that means to add up the sum. The N here is going to mean the coefficient for whatever side of the equation we're on. In this case, we're always going to have products minus reactants, okay? Just like when we did the earlier calculations in this chapter, we had final before initial. So you could think of it that way. We're having products minus reactants, okay? It's always going to follow that format. And the N is going to refer to the coefficients of products here on the far left side. And then the N in this case is referring to the coefficient of the reactants from that reaction. So let's go ahead and look at an example so that we can really visualize this process. Okay, so it says, example number 11, calculate the delta H standard for the reaction for the following using these given values. And so we're given our overall reaction there, CH4, that's methane, plus oxygen. We have 2 moles of oxygen, and we're going to create 1 mole of carbon dioxide and 1 mole of water. Okay? We're given 3 partial reactions, 3 steps to get us to that final product. And so we have carbon elemental by itself, okay, in the form of graphites. We're not doing diamonds here. So we see the S for solid. The first step reaction, we have it reacting with hydrogen, okay, and we're going to get methane there. And so here's an example of where we're creating a reactant that shows up in our overall reaction. Right, so this step has to occur first. Just taking some carbon, take some graphite out of your pencil, ignite it in the presence of hydrogen gas, you're going to make methane gas. Now that's going to be used for the combustion that we see up at the top. Okay, secondary reaction, we have some elemental carbon reacting with oxygen, and we're going to get CO2 from that. Okay, and then finally we have a second reaction. We could take the hydrogen that's formed up here in the first step, and we could bring it down. Whoops, sorry about that. Click there. You go back. Our hydrogen in the first step, we can look at it. What else is going on? This is all occurring in the reaction beaker or the reaction flask. It's all happening. We're used to seeing just here's the start, here's the end reaction, but in actuality, this is what's occurring. It may be fractions of a second, but this is what's truly happening in that container that you're doing a reaction in. We have some hydrogen reacting with oxygen. We're getting water vapor out of that. Right? So each of these partial steps is going to lead us to this overall reaction up top in bold. And so each of those partial steps here have their own delta H standard of formation. And so if we want to calculate for the reaction, what we're going to need to do is what we did for the previous example. We're going to need to flip some of those steps so that they line up properly, and we're able to just kind of add the steps downward and get the CH4 only on the reactant side, get just the O2 on the reactant side, and then we want the CO2 and the water to only be on the product side. So if we need to reverse a reaction, we can do that. Okay, and then remembering when we do that, we do need to flip the sign of the delta H. Okay, and so doing that with two of these steps, we get the methane on the reactant side. We have the carbon elemental cancel out. We have the hydrogen cancel out. And we're left with the methane here. So that's partial. Let's take a look at it all together here. So here is where we would write, here's our overall reaction now. Okay, we've added up the delta H's from those three initial steps, and we're going to get negative 802.5 kilojoules. Now we would plug this into the summation formula. So again, it's products minus reactants. So our products are carbon dioxide and water. Let's follow that down here. See how they're being plugged in over here on the left. They're being plugged in first. That's the products. So we're taking any coefficients here, bringing them down, and multiplying that through with the values. We're going to have to look up these values. The delta HF formation for carbon dioxide, water, methane, and oxygen. And so when we find those values, we plug those in. We do the order of operations, we combine like terms, and we arrive at the answer here. All right, so that is the end of chapter 7. So I'll just give a brief pause here and I'll make a new video for chapter 19. If you have any questions, please make sure to write them down. You can send them to me in an email, and you can also hold them for when we see each other again. That is going to be a few days, though, until Monday. So whatever you're comfortable with, but please send those questions along and hang tight. I'll be right back with the chapter 19 notes.